So I'd like to welcome everyone. I'd like to introduce Sara. Sara is a director at Trillium Technologies and is giving a talk titled Next Gen Lunar Explorers, the Rise of the Super Intelligent Autonomous Rovers. So very excited to hear this. It's off to you, Sara.
Great, thank you. As you said, I'm Sara Jennings. I'm also the executive producer for Frontier Development Lab and a master's student at the University of Boulder, Colorado. And I'm joined today with my colleague, Ignacio Lopez Francos, who's a faculty and research lead at Frontier Development Lab. And we're here to talk about the next generation of lunar rovers. So I wanted to start out by sharing why will our next generation of rovers be more intelligent than ever before? Well, first off, we have more data and information than we've ever had. We also have more tools like different machine learning techniques, and we have more capabilities, for example, compute capabilities. And all of these things together are going to lead to our next generation of super intelligent autonomous rovers. So I'd like to go into what is Frontier Development Lab and how are we furthering research for the next generation of rovers. Frontier Development Lab is a public-private partnership between NASA and the SETI Institute and leaders in commercial AI and private space. Frontier Development Lab brings together PhDs and postdocs from both machine learning and domain science and exploration expertise. And we pair them together to be able to work on challenges like in the various verticals that you see here below. We also provide our researchers with massive amount of compute so that they can do research in an accelerated amount of time. So today, of course, we're going to talk about the work that we've done in space resources. I'd also like to mention that we have a partnership with the Luxembourg Space Agency and the Space Resources Initiative. So the Space Resources Initiative was announced in 2016 and really set Luxembourg on the map for research in space utilization or space exploration and resource utilization. And we are excited that they are a partner with us, and they've provided both challenge support as well as researchers for our program. And here's a timeline of our research progression on lunar work. So today we're going to go through our work from 2017 to 2020 and tie that back to how this is supporting our next generation of rovers. So starting with 2017, we had a team of researchers, Dietmar, Eleni, Tony, and Timothy, and they set out to work on lunar mapping. So the moon is really hard to be able to map because there are permanently shadowed regions, there's slight changes in the surfaces of the moon due to micrometeorite bombardment, and there's also a lot of shadow changes. So what they found is this is a really difficult task, and they were wanting to be able to automate crater detection. And it gives you a feel for how difficult it can be. So being able to tell the difference from these images if that's a crater or not. So what they developed was a crater extractor for both the polar and equatorial regions. And to do this, they developed a feature data set where they labeled and annotated a whole bunch of both visual imagery as well as digital elevation models, and we're able to develop an automated crater detector using a convolutional neural net. And their convolutional neural net at the time was able to have a higher accuracy than the state of the art in algorithms, as well as the time that it took to identify craters in 1,000 images was at around a minute. Compared to the time it takes a human, which would be around 1 to 3 hours. From there, they were able to take both the visual imagery and the digital elevation models, and they were actually able to start overlaying those to start out the mapping process. So I'd like to move on to 2018. So in 2018, we had two projects. One was focused on localization, and the other one was focused on cooperative robotics. So for the localization team, we had Andrew, Phil, Ross, Benjamin, supported by a team of mentors, including Sylvester and Timothy. And we also had Phil Metzger that was supporting. And really their task was, once a rover lands on the moon, how do you help it localize and know where it's at, since there's no GPS? So to do this, you need a lot of data. So what they did is they developed a synthetic data set of over 2.4 million images of both reprojected views of what the rover sees. So you can see that here, which is 360, as well as the true orbital views. And so they were able to take this information and then develop an algorithm that could identify the 5 best matches compared to where it was actually located. And they were able to do this because they had the ground truth, since it was a synthetic data set. And this localization work is being continued by one of our researchers, Phil, who works for iSpace and also is a PhD researcher at the University of Luxembourg. Then the other team in 2018 focused on cooperative robotics. So this team, Drew, Zahi, Francisco, and Anna, were tasked with, in the future when we have multiple different rovers on the moon, that would like to accomplish a science mission task, how do you utilize them in the most efficient way possible? So what they came up with is automated trajectory planning for multiple rovers on the moon. So they essentially took in points of interest for different science and research missions, and they used a path planning algorithm called A-star. They also combined this with information from maps, so taking into consideration things like slope, shadows, and the communication coverage, and developed a cost generation map, which was able to output a trajectory proposal. So here is some of the information, like I said, that they took into consideration for that cost generation map. So the digital elevation model helped them identify the communication coverage, slope map, and time-dependent shadows. And here is a visualization of essentially how their algorithm works. So you can see there's multiple different points of interest. You have a relay rover, a science rover, and it's communicating also with the lander. So depending on the slope, shadows, and communication, it determines which rover should go to which location at what point in time. And that takes us to 2019. So I'm going to go ahead and turn it over to Ignacio to talk about that work.
Thank you, Sarah. So in 2019, we focused on answering the question, can we develop high-resolution lunar resource maps that could help NASA and other space agencies and commercial partners allocate resources for future robotics and human lander missions? Next. So with the help of these 4 talented researchers they see here in the image, Valentin, Jerome, Ben, and Nikki, we took on this challenge last year, next slide, sorry. Yeah, so we're going back to the moon, right? For my generation, this is a very exciting moment to see in our lifetimes. And actually tomorrow we're celebrating the 51st anniversary of the landing of Apollo 11. And now with the Artemis program, NASA is leading us into the next era of moon exploration, and with plans to put a man and the first woman on the moon by 2024. Next. And this time we're not only going to the moon, but we're also planning to build a long-term, permanently lunar base where humans can one day stay. But in order to really achieve this monumental feat, a significant amount of resources are going to be needed to be extracted from the lunar surface. Now, it will be really difficult and very expensive to send all these resources from Earth to the moon. So it's crucial that we understand what resources are available to us existing on the lunar surface. Next. Metal is going to be a key resource for this sort of missions, and metal can actually be deposited on the surface of the moon in the form of meteorites. So this is, for example, an image taken by the Curiosity rover on Mars, and it's essentially just a big chunk of iron and nickel sitting on the surface. And we've actually found similar sorts of meteorites here on Earth as well. So we can find the location and find a way to detect where these metals are on the lunar surface. It would be really massive step forward in our goal to build a sustainable lunar base. Next. So the challenge was to be able to detect these metallic objects found on the surface of the moon. And what you see here is a crater called Tycho on the near side of the moon. Tycho is quite massive. It's around 80 kilometers across. Next. And for scale here, you can see the Golden Gate Bridge that looks quite small in comparison. Tycho is also very deep, around 5 kilometers deep. And even with the resolution of this image, if we zoom in, we wouldn't be able to distinguish a metal object from a normal rock on the surface. So what we need is more data and more information to do this comparison. Next. Next. So we solved this issue by collecting data from 6 different spacecraft, which include 12 different instruments that cover different portions on the electromagnetic spectrum. Next. So we cover, no, before, sorry. Go back one more. We basically cover ultraviolet, visible, microwave, gravity, gamma, magnetic, and thermal instruments, and we combine them all into a stack to be able to then distinguish a metallic object from a rock, for example. So this means that we can have an amazing imagery like here, Tycho, as you can see here, connect. And then we combine it with an elevation model that gives us information of the relief of the moon terrain of the lunar surface. And here the blue colors indicate the low elevation and brown colors indicate the high elevation. Next. And we can also use maps that tells about the rock abundance, where red colors in this case indicate rocky areas with a higher concentration, and blue colors indicate lower concentrations, which are smoother. Next. And we can also overlay a map of the average surface temperature. And here we indicate in red the areas of hotter areas, and in blue and green the colder areas. And so by fusing all these different data sets, each of them telling different properties of the terrain and composition of the surface of the moon, the team was able to create this massive stack of lunar orbital measurements composed of over 40 layers and multi-sensor data, which occupied around 35 terabytes of data. And then with this, it allows us to also apply machine learning techniques like anomaly detection on top of it. Next. So the goal of this project was to find metallic signatures on the surface of the moon without exactly knowing how what these metal signatures look like. So we approached this problem by using all the computing power that Google Cloud provides us to look for patterns in the data from previous lunar missions. And then we decide to just focus on those maps of the moon that tell us something about the optical, thermal, and magnetic properties of the surface, because these are the properties that we believe were the most closely related with these metallic signatures. And what we found from analysis was that we could isolate 7 distinct patterns in that data, and each of which is related with a different anomaly. And when I say anomaly, what I mean is that one area of the moon, for example, might be particularly bright, or it might have a very strong magnetic field, or it might be very hot, and so on and so forth. And to give you an example of this, in this slide that I'm showing right now, we can see 4 different craters where we detected some of these anomalies. So on the top, we have Marius A, which has a very bright center in the visible range, but it's not as bright in the infrared range. Below, we have Hell-Q crater, which overall is very bright, but has the center particularly highly bright and with magnetic anomaly. And on the top right, we can see Giordano Bruno, which has a bright center, but its surroundings are actually quite dim. And the last example on the bottom right is Galois, which has a very strong magnetic anomaly. And with this slide, we wanted to illustrate was that we can use these anomalies to distinguish between different craters. And this is very exciting because it allows us to create a crater catalog that we can then use to classify those craters. And we think that this is also a very powerful result because once we find a certain metal in one of these classified craters, it will immediately inform us about the likelihood of finding the same sort of metal in all the other craters of the catalog. Next. So a smart way to search for metals by looking at the temperature of the surface of the moon. So as we know, metals have a high thermal conductivity, and so they're really good at absorbing heat and fast, very fast in particular. So we use this thermodynamic property to check for variations of temperature throughout the lunar day. And so to search for metals, we calculated the gradient of temperature for each pixel in our image and search for regions where their value was very different to their surroundings. And so we trained our machine learning model on all this existing thermal data, which was collected mainly from the diviner, to search for these anomalies that could indicate location of these metals. So this is again Tycho crater. And what you can see on the right hand is a thermal anomaly map that was generated by our machine learning model. And the bright yellowish areas tell us where the model thinks is more likely to be these thermal anomalies. And what's really interesting is because we can see, for example, the bright spots at the center of the crater and also in the western rim. And so these types of anomaly maps, together with the stack of over 40 layers of lunar orbiter data, were very powerful and are of very high scientific and commercial interest because it can help us better understand the geology and history of our moon. And it can also help us plan for future human and robotic missions in the search for metallic resources. Next. So, okay, now we know that metallic resources are important to create infrastructure needed to establish base camp in the moon, and maybe even creating a new space mining industry. But amongst the resources that we can find on the moon, there's one resource that without it, it will be almost impossible to make our space exploration ambitions a reality, and that is water. Next. So why? Water is an incredible, viable resource. It has two critical functions. So first, for the astronauts to survive on the moon without the need to carry it from Earth, and second, as propellant. So we can use electrolysis to break down water molecules into hydrogen and oxygen to form fuel for rockets. And essentially, we can use the moon as an interplanetary gas station for trips to Mars and elsewhere. Next. So this year, our team is focusing on answering the question of how can we improve our understanding of the presence and distribution of the lunar water ice, and how can we help plan more effective ground missions to explore and retrieve this vital resource. Next. So as the moon has no atmosphere, its temperature budget is controlled by illumination only. So this means that volatiles like water are going to accumulate in the so-called cold traps, which are regions that never see the sunlight. This image right here is a sequence of wide-angle camera images captured by the Alrock orbital satellite over the south pole of the moon. And what we can see is that certain craters are in complete dark. These are areas that we call the permanently shadow regions, or PSRs. Next. Next time. So we have a good idea of where these water ice areas are on the surface. For example, one back, please. On the left image, there you are. Yeah, on the left image, there's a neutron count map, which indicates the presence of hydrogen. And if we zoom in on the right side, we see that these regions are of higher concentration that fall under what we call the permanently shadow areas, which are dark, the completely black. So we have a good idea on a regional scale of where we can find water ice, but we don't have a good precision, which is in a sub-hectometer scale of the location of these resources. So we consulted for this project with different teams at NASA that were developing the Artemis mission, as well as our partners, Luxembourg Space Agency, and we identified these as one of the bottlenecks. So our work this year is helping the identification, localization, prospection, and extraction of water ice by improving the quality of Alrock narrow angle camera images over the permanently shadow regions. Next. And we'd like to know where exactly is the ice in the PSRs and how can we get there safely. So by using this improved image that we are aim to produce, we'd like to understand, for example, is the water ice located in the pristine regolith, or is it maybe in other rocky areas, and how accessible they are? Are there any hazards in the path that we could we should know, for example, like cracks or big boulders that could put the risk of the rovers during this traverse? Next. Here we can see a screenshot of the quick map tool. In particular, this is a mosaic over 1,000 from narrow angle camera images aboard of the Lunar Reconnaissance Orbiter. And they all overlap over the Shackleton crater, which is one of our target PSRs. Next. So here's, we took a look at the metadata from those images. The metadata actually describes the conditions in which the images was taken. And for example, we have a spacecraft altitude. We also have the solar incidence angle of the images. So for example, when you get to the poles, the incidence angle is more skewed towards 19 degrees. That we can see that on the top right chart. On the right, we put a little animation that shows you the variation of the incidence angles for the same location. And then on the bottom right left images, we include metadata such as exposure and spatial resolution, which we know are correlated with the quality of the images and therefore are important for our work. Next. So you may wonder if the PSRs don't receive any sunlight, how can we actually look into them? So the strict definition actually is that they don't receive any sunlight directly from the sun, but they do receive some scattered light from the surroundings. Basically, it's the reflection from the rocks. And if you look at the raw image of the PSR, which is the one in the left, the region of the PSR that is very dark, you can see this, and then they can see the surroundings of the crater on the top. And by simply increasing the contrast of the image, we can actually start seeing some signal inside of these PSRs. Next. And this is another image on the other side of the crater, of the same crater. And here we can better appreciate when we increase the contrast, what appears to be a systematic noise. And that noise affects our ability to understand what topographic features this area have. So one of our goals is to reduce the noise of these images. Next. The PSR I saw before is closer to the equator, but this one from the Shackleton crater is closer to the South Pole and at a very high latitude. And you can see here that the level of noise is very intense and really inhibits our ability to see what's inside of the PSR. So an improvement here would be really beneficial to understand what's inside of this PSR. Next. Okay, so here is some images. We zoom in into this PSR image that I saw before. This is the noise. And here's can we look, you can see it actually looks very systematic and very structured. And so one of our initial approaches was to look to see if there's any correlation between the metadata of the images, like exposure, duration, or orbit number, or the temperature of the instrument, and the image itself. So we can train a machine learning model to be able to learn to characterize this noise and use that to later help us remove the noise. Next. Another approach that we want to test is to improve the images by increasing their resolution. So for example, we have these two images of the same location. The one on the left was taken with a lower exposure time. And so it's with high resolution, it's around 2 meters per pixel. Usually raw would be mostly dark, but we have increased the contrast here so you can see some signal. And then on the right side, we have for the same location, but with a higher exposure time. In this case, 20 times higher. 10 times higher. And this decreases the image resolution to a magnitude of around 10x as well, or around 20 meters per pixel. So the idea is to use also machine learning techniques and train a model that is able to map a low resolution image to the high resolution pair. And then we can see that we can enhance the resolution of the images that we have with lower resolution. And next. So here, I just want to show you some preliminary results that we have using the generative noise model. So the first approach. So we take, for example, the image on the left, which is raw, it's an EDR image. And then we were able to predict noise, which will be the image on the right, and then subtract it from that image. And therefore, we get the resulted image on the center of the frame. And these are very early stages of our project, but the results want to be very promising. So we are looking to have some final results probably by the end of next month. So stay tuned. And next. Okay, so with this, we are hoping that with these 5 examples of our projects from our lab, we can give you a good understanding of the challenges that we are and will encounter on our space exploration ambitions. And also some of the solutions that also characterize for having massive amounts of data, state-of-the-art intelligence algorithms, and also high-performance computation like GPUs and edge computing. So we think that by harnessing the power of this combination and bringing in talent researchers from both on the machine learning side as well as from the planetary science side, we can help increase the understanding of our moon and the space in general, as well as can help us advance the autonomy requirements for future rovers that will be sent to explore the moon. Next. And with that, I just want to conclude our presentation. I also would like to thank the organizers for the opportunity to present our work in this forum, and also for everyone for listening. And if you want to learn more about our work, Frontier Development Lab, please visit the link on the bottom. And you can find all the proceedings for the work that we touched today as well. And I think we'll be hanging around here in case there are any questions. So thank you very much.
Thanks for that. That was awesome. And yeah, we can open up the questions now. So if you have any questions, please post in the chat or raise your hand, and we can unmute you and you can ask your question. No questions? Oh, here we go. Chris says, thanks for your time. That was a lot of information. I agree.
Yeah, definitely very welcome. And like Ignacio said, there's more detailed reports, papers, tech memos, and posters that are all on frontierdevelopmentlab.org for all of the years that we talked about. So if you want more detailed information and time to process, that's the place to go.
Well, looks like we got a couple of questions. Are you open sourcing your research?
That's a great question. So the answer is yes, and we're actually working on putting, as Frontier Development Lab, we're working on making the data sources that we've created across all of our projects, not just the lunar ones, more publicly available. So that's something that you can definitely stay tuned for. Generally, we open source our research after our researchers have had the chance to do any publications or any other continued research. Ignacio, I don't know if you want to add on to any of that.
Yeah, no, that's exactly what I was going to say. For example, the projects from last year will be open source, hopefully some point this year. I know the researchers are still working to finalize everything, but the goal would be to actually make all this data set available, as well as the anomaly maps. And yeah, for this year, it usually takes some time for peer review, and also all the researchers are encouraged to submit papers. So probably over the next few months, we'll be submitting papers of the work for this summer to planetary science, as well as artificial intelligence conference. So yeah, I would say within a year, probably we'll share some results of our work for this year as well.
Okay, thank you. I think we've got time for a very quick, another quick question, but we've got 1 minute. So how would a lunar GPS system improve navigation on the moon? Is it needed? A question from Paul.
Yeah, so the example that we saw here, the absolute localization, essentially is because we don't really have GPS on the moon. So what we're using is different techniques to really locate ourselves. So one of the interesting areas is actually taken from autonomous driving here on Earth, would be to start showing in the project. It's like, can we match satellite imagery that we have, that we currently have around 1 meter per pixel, except for obviously the PSRs, to images from the panoramic view. And then one of the good things of the moon is that the terrain doesn't really change, so that we can map some boulders that we found, some rocks, to the satellite images, and then we know with more precision where the rover is located. So that can help, for example, locate specific areas where we want to drill, with a higher precision. Also, it can help navigate and maybe don't, crash or avoid obstacles we have detected pretty in advance. So these sort of things can help.
Okay, thank you very much. We have to wrap it up now, but I'll see you all around in the conference, and thank you, Sara. And sorry, how do you pronounce your name?
Ignacio.
Ignacio. Okay, sorry about that. Thank you
No
for the
problem.
presentation.
Thank you.
Great. Thank you.
Yeah.